Welcome to Old School Chemistry. Today we're going to do the ALEKS topic, calculating an equilibrium constant from an equilibrium composition. Let's look at our formula for equilibrium constant. The equilibrium constant is always going to be products divided by reactants. So I wrote our generic equation here. We have little a plus big A. Remember, the lowercase letters represent your coefficients and the uppercase letters represent whatever your chemical species is, the compound or the element. Plus little b, big B in equilibrium. Remember, equilibrium means we have equal rates for the forward reaction and an equal rate for the reverse reaction. I do this a lot with my students, equal rates. We're going forward and reverse. So this is going to be an equilibrium with our products, little c plus little d, big D. Now products divided by reactants is going to be the concentration, so this is the molarity. Remember this M right here means molarity. It's going to be the molarity or pressure, ATM. Those are the two units that we can use when we're doing our equilibrium. So it's going to be the concentration or the molarity of the product raised to the power of its coefficient. So whatever this coefficient is, that becomes the power. And this is the D, concentration of D raised to D, divided by our reactants, so A raised to the power of A, whatever that coefficient is, times B raised to the power of B. I also like to emphasize every once in a while, I'll see students put a plus sign right there. These are not adding or subtracting, they are multiplying. They're multiplying. So let's take a look at this one. It says the hydrogen chloride and oxygen react to form chlorine and water like this. So there's our balanced chemical reaction. Notice those coefficients. We're going to need them. They're going to become the exponents. Also, the chemist finds at a certain temperature, the equilibrium mixture of all of these species have the following composition. Ooh, look, we are in ATM, which is great. You can totally use ATM. The one thing that changes on this, instead of having concentration, is you do partial pressures. So I'll write this out symbolically with partial pressures. You can use both, okay? We can have concentration or we can have partial pressures. This is sub C for concentration. I'm going to do Kp for pressure, and this is going to be the partial pressure of my products, partial pressure of Cl2, and what's that coefficient? A 2. So that will be squared times the partial pressure of my second product, water. That coefficient is 2, so this is squared, divided by reactants. We're going to have the partial pressure of HCl. That coefficient is 4, so that's to the fourth power, times the partial pressure of O2, and that coefficient's a 1. I can leave this blank and it's understood to be a coefficient of 1. Now, if these had been concentrations, if they had given molarity, I simply would have put here the Cl2 in brackets squared times the H2O in brackets squared. I would have just put those molarities, I would have put the compounds in brackets indicating we're using molarity. So you can use both, okay? Now we simply plug in the numbers. Let's see what we get. Kp is going to be, my Cl2 is 4.19, that's the partial pressure squared, times H2O, 3.20 squared, divided by the HCl right here, 18.5, and that was, wow, to the fourth power. And then we have a huge number for oxygen. Partial pressure is 93.9 ATM. Now a reminder for you, our Kc and our Kp, the equilibrium constant, is unitless. There's no unit on it. It's just the ratio that when you hit beautiful forward and reverse equilibrium, what's the ratio of those products to reactants? So I plugged this into my calculator, kind of hefty, right? A lot of big numbers. Here is what I got. I got that our equilibrium constant is going to be 1.63. I had 3 sig figs, I'll do 3 sig figs here, times 10 to the negative 5. Great, and so that's what I type right down here, is that, should we type it in? Let's do our 1.63 times 10 to the negative 5. Me being a teacher, I want to pull one more thing out of this. Notice this number, our K value, is less than 1. So what does that mean? when I reach beautiful equilibrium, the forward rate equals the reverse rate, and the ratio of products over reactants is less than 1, is this product or reactant favored? If it's less than 1, it means you have more reactants. This is going to be reactant favored. And then, of course, the opposite would be true. If K is greater than 1, it means you have more products when you reach equilibrium. That would be product favored. The reason why I bring this up is the number one misconception on equilibrium for students is they think equilibrium means equal amounts of products and reactants. That's not it. Equilibrium is equal rates. The rate at which reactants change to products equals the rate that products go back to reactants. And when you reach equal rate, you have constant concentrations, but not equal. Okay, not equal amounts of reactants and products, but constant amount of reactants and products. Okay, so good. Well done on this. Super straightforward. You just do products divided by reactants, take the coefficient, becomes the exponent, plug and chug. You've got it. Have a great day. Thanks for being here. Bye.